Hello everyone. This video is about the Knewton Alta assignment for section 9.2 called Simplifying Square Root Expressions. So in this video, I'm going to be going over a preview version of this assignment. So please understand that the questions I see in this video may not be the same questions that you see when you work on the assignment on your own. Pardon me. But the objectives are all the same. The structure should be similar. So I'm hoping that watching me do these here helps you out when you're working on these on your own. Alright, so on the assignment page you should be seeing the title, the mastery bar telling you how far along you've gotten, the objectives. Looks like there are 3 objectives for this assignment. Under the current objective, there should be a question related to that objective. And at the bottom of each question, you should see a feedback button where you can send feedback to Knewton if you wish. You will not have this instructor cheat button. It's for instructors only. But you will have this more instruction button. If you ever feel like you're struggling with a topic or a particular question, click on this and you'll be taken to a page with some reading or videos to study and given some questions related to that instruction. And completing those questions is another way to progress through the assignment. Pardon me. Alright, so before I get into any of the objectives here and questions, I want to talk about the properties mentioned in these objectives. There's the product property and quotient property for square roots. Alright, so let me get into those real quick. So first, the product property. For square roots. So this is if you have the square root of a product. So inside the radical symbol, inside the square root symbol, you have a product. A times b, let's say. Or a times b times c. It doesn't matter how many factors the product has. This will be equivalent to the product of the square root of each factor. So the square root of the first factor times the square root of the second factor. As long as those factors represent non-negative numbers. Okay, we need the square root of a and the square root of b to be real. And you may recall from section 9.1 that if the radicand or the number inside is negative, then we have an expression that's not real, and we don't want that. And then the quotient property is very similar. Right. It's just the square root of a fraction. Right. So the quotient property for square roots, if you're taking the square root of a quotient, let's say a divided by b, this can be rewritten as the square root of the numerator divided by the square root of the denominator. Again, as long as a is some non-negative number and b is a positive number, right? Because b can't be 0 because it's in the denominator. Right? That's why I've got b strictly greater than 0 here. Because if either one of these is negative, this right side will have some non-real part of the non-real expression, right? The square root of a negative number is not real. We're only dealing with real numbers here. All right, and then of course I'm assuming you have gone through section 9.1 on, working with square roots of perfect squares, and you know what perfect squares are. So I'm not going to get into all that again. But now we're just adding these two properties to what you learned in section 9.1. Alright, so in the first example I'm given, we're asked to use the quotient property to simplify a perfect square fraction. So some perfect square, something that can be written, to the second power. That's what a perfect square was, right? Something that can be written to the second power nicely is going to result from this fraction here, as we'll see. So I'm going to write out this problem. We're given the square root of 192 y to the 17th divided by 3y to the 5th. Now, if you actually divide these, you're going to get that perfect square that they were talking about. This ends up being just the square root, and then 192, divided by 3. Well, it's not totally a perfect square, but the y factors will form a perfect square. You'll see in a second. But 192 divided by 3 is, 64, which is a perfect square. So I was misspoken. 3 times 64 is 192. And then y to the 17th over y to the 5th would be y to the 12th. Right. And then remember, what we're asked here for is the square root, the principal square root, right? The result should be non-negative, of 64y to the 12th, which is the square root of, and then, again, I'm trying to think of how to write this expression inside the symbol as a square, something to the second power. Well, 8 squared is 64, and then y to the 6th squared would be y to the 12th. Remember that power to a power rule. 6 times 2 is 12. And so I end up with, now if you recall my last video, section 9.1, remember the square root of some expression squared is technically supposed to be the absolute value of that expression, because this is the principal square root symbol. The results should be non-negative, thus the absolute values around it. So technically this should be the absolute value of 8y to the 6th. But, this is an even power on y, and if you take any real number raised to an even power, it's not going to be negative anyway. So since this expression is not negative anyway, the absolute value symbols are not necessary. So this will just be 8y to the 6th. Now you can also see from the instructions, they're telling us in all these problems, or at least this one, you may assume any variables are greater than 0. So they're already telling us that the variables are representing numbers that aren't negative, they are positive. So this expression represents a positive number, so I don't need the absolute value symbols at all. So the final result here would be 8y to the 6th. Not 8y squared, 8y to the 6th. And then, after you submit an answer, you'll be told if you're right or wrong, and then given some sort of answer explanation. Please read through the answer explanations just to make sure you understand why something was correct or incorrect, and hopefully you can learn from your mistakes for future questions. Alright, so here's another one like this, where I'm asked to, simplify a perfect square fraction. So I feel as though once we simplify this fraction, there will be some nice perfect squares in here based on the name of the objective. So here I have the square root of 1,350 divided by 600. Okay, now I can take away the tens, right? Divide 10 out. So that becomes the same thing as 135 divided by 60. And, I'll just take it one step at a time here. And 5 is a common factor here. 5 actually goes into 135 27 times. And 5 goes into 60 12 times. And these even have a common factor of 3. So reducing even further, 27 is 3 times 9. And 12 is 3 times 4. And this is definitely perfect square divided by perfect square here. Now I can apply that quotient property if I want. Take the square root of the numerator, right? The square root of 9 divided by the square root of the denominator, right? The square root of 4. And don't forget, this is the principal square root, the positive square root. So don't put plus or minus, right? This is supposed to be positive. Positive 3 is the square root of 9. And this principal square root of 4 is positive 2. So my final result here is, 3 halves, right? 1.5. But they ask us to give the answer in fraction form. So this all simplifies down to 3 halves. Okay, good. All right. All right, so now we're asked to use the product property to simplify square roots. So remember that product property was this. Right, the square root of a product is the product of the square roots of the factors, as long as the factors represent non-negative numbers. Now when they say simplify a square root, this means that we want to eventually get it to the point where the expression inside the expression inside the root, which is called the radicand, has no perfect square factors other than 1. Right, other than 1, because the number 1 is a perfect square. It's 1 squared, and it goes into everything. So it has no perfect square factors other than 1. So here we have the square root of 200 times z to the 13th power. And we're asked to simplify this. Write it so that the expression inside the root symbol, the radicand, doesn't have any perfect square factors. Now remember, perfect square factors are basically things with even powers. Right? Something that can be written to the second power, right? So something squared, something to the 4th, the 6th, the 8th, all that stuff could be written as something to the second power very nicely. All right, so what I'm going to do is I'm going to factor the radicand in the following way. And this is what I'll do for all the problems where we're asked to simplify the square root. I'm going to factor this radicand, this 200z to the 13th. I'm going to write it as a product. I mean, I know it's a product already, but I'm going to write it as a different product. I'm going to factor the radicand as perfect squares, right, perfect square factors times non-squares. And I'll show you what I mean. So it's the square root of, now if you want, you can break down everything to a product of primes. Just break everything down completely. Like, 200 is 2 times 100. Well, that's just 8 times 25. That's 2 to the third times 5 squared. All right, that's 200. 8 times 25. If you break it down completely. Times and then z to the 13th. And then here's what I mean by the split. I'm going to say this is equal to the square root of, and then I'm going to put it in two different sets of parentheses here, two different factors. 2 to the third power is 2 to the second, right? That's a perfect square, times 2 to the first. I'm just putting the highest even power that goes into the power on the factor on that base here, and then the remaining stuff in the other factor. 5 squared, that's an even power, that's a square. So that goes inside the ones with the squares, right? And then z to the 13th I can write as z to the 12th, right? The largest even number that is less than 13 is 12, times z to the first. So the perfect squares that are factors of this expression are 2 squared, 5 squared, and z to the 12th. And then 2 times z, those aren't squares. And then I apply the product property. Right, then I apply that product property. And what I'm going to do is I'm going to write this as squares, right? This is the square root times another square root. Then 2 squared, 5 squared, z to the 12th is 2 times 5, or 10, times z to the 6th squared, right? Because 2 squared times 5 squared is 100. That's 10 squared. And then z to the 6th to the 12th would be z to the 12th. There's the perfect square in this first factor. And then the stuff left over, the 2 times z, that's going to stay in the square root symbol in the other product, in the other factor. Right, and then we do the square root of a square. Those just undo each other. Now, again, technically, I should write absolute value of 10z to the 6th, but again, they're telling us to assume that z is positive. So I don't need absolute value symbols, and you would also not need absolute value symbols because it's an even power on z. That'll be non-negative no matter what. So this square root simplifies to just 10z to the 6th times the square root of 2z. And there we have it. This radical expression here, this square root expression, is considered simplified. Even though it takes more probably to write this than it did the original, but it's considered simplified because the radicand, right, the expression inside the symbol 2z, has no more factors that are perfect squares. And if you'd like to test this out, just replace z with some numbers that are positive, and you should punch this in a calculator, punch this in a calculator, replace z with any number you want that's positive, and they'll give you the same value no matter what. But I'll leave that to you to check. All right, so I end up here with 10z to the 6th times the square root of 2z. Make sure that 2z is all in the square root. Wonderful. Again, you see how they broke it up to 100z to the 12th times 2z. That's a perfect square times something that's not a perfect square. That's exactly what I'm going to be doing this entire time. All right, we're asked to simplify a square root. All right, so quotient property to simplify square roots. All right, and again, they're telling me to assume all variables are positive numbers, so I won't need absolute value symbols at the end. And again, I'll write this out, and yeah, I'll start factoring the numerator, factoring the denominator, and break it up into perfect squares times non-perfect squares. Right, you'll see. Like I said, I'm going to be doing that for pretty much most of these exercises. So we have the square root of 272 times p to the ninth over 324 q to the second. Alright, so I'm going to do some factoring here. 272, do some factor tree stuff. This is 2 times 136, and 136 is 2 times 68. Alright, 120 plus 16. Yeah. This is 2 times 34. This is 2 times 17. Alright, and that's it. Alright, so this ends up, this is 2 to the fourth power times 17. Alright, and I'll incorporate that into my problem in a second. Then 324 is 4 times 81. I can see that right now. 320 plus 4. And then 4 is 2 squared. 81 is 3 to the fourth power. I just know that. Alright. So 324 is 2 squared times 3 to the fourth. Alright, 4 times 81. Alright, so I'll write that out. So we have the square root of, 2 to the fourth times 17 in the numerator times p to the ninth as well, divided by, and then, 324 is 2 squared times 3 to the fourth, and then you have q squared in the denominator. And I can cancel some stuff here. You see that they have the numerator and denominator have common factors of 2 squared. So both the 2's will cancel on here, and just 2 of them will cancel up top, so it becomes 2 squared now, or 4. Alright, so now I'm going to apply that quotient property. Alright, where we take the square root of the numerator. So it's the square root of, 2 squared times 17 times p to the ninth divided by, and then the denominator is just the square root of 81q squared. I know that those are perfect squares already, so I can get that no problem. And then I'm going to apply the product rule, the product property to the numerator. This would be the square root of, 2 squared is 4 times, and then p to the ninth. 17 is the first power. There's no perfect square in that. P to the ninth, though, I can break up as p to the eighth times p. Alright, so here are my perfect squares, and then the stuff that's not perfect squares, the factors that aren't perfect squares, are just 17p left over in the other square root. Right. So again, 4p to the eighth times 17p would be 4 times 17 times p to the ninth. Perfect squares in one square root, not perfect squares in the other. Now the square root of 81q squared would be 9q, or technically the absolute value of 9q, but they told us to assume variables are positive, so I don't need the absolute value. So I got 9q in the denominator. And now I'm going to actually simplify. Now the square root of 4p to the eighth would be 2p to the fourth. And then you have times the square root of the non-squares, right? 17p. So there's the numerator, and the denominator is, 9q. And again, no need for absolute values around any of this, because they told us to assume that all the variables represented positive numbers. Wonderful. Alright, so in the numerator, 2p to the fourth times the square root of 17p, and then denominator 9q. And this should be good. Great. Okay. So back to the product property to simplify square roots. Again, I'm just trying to rewrite it so that the square root expression, the radicand, has no factors that are perfect squares. So we have the square root of 242 c to the 29th. Now I'm going to break this up to a square root of perfect square factors times the square root of non-perfect square factors. Now 242 is 121. That's 11 squared times 2. So 11 squared times 2. And then c to the 29th I can write as c to the 28th, right? Anything with an even power is a perfect square. Times c. Right, so c to the 28th in one radical, c to the first in the other. And then I simplify, this would be 11. The square root of c to the 28th would be c to the 14th, right? Because c to the 14th squared would be c to the 28th. So I have 11 c to the 14th times the square root of 2c. Right? And this expression here should have the same value as this expression I started with for any positive value of c. Right? I'd have to replace c with a positive number. And that's what they're telling you here, right? Assume that c is greater than 0, right? Assume that c is positive. So 11 times c to the 14th times the square root of 2c, and make sure the whole 2c is under the radical, under the square root symbol. Wonderful. Okay, back to quotient property. Alright, so I actually saw these numbers. Well, we saw 272 and 324, right? So these are different. All right, but again, I'll write this out, and we'll do some factoring and simplifying of the fraction first before we use the quotient property and then the product property to simplify the square roots. So I've got a square root of 384 u to the 5th times y in the numerator, and then 242, which we saw in the last example, times u squared times y to the 13th. Alright, so once again I'm going to do some factoring over here. Alright, 384 is 2 times 192. 384. This is 2 times 96. 180 plus 12. 96 is, 3 times 32. Okay, and I know that 32 is 2 to the 5th power. So we have 2 to the 5th, 6th, 7th. Right, so this is equal to 2 to the 7th power times 3. Right, the only other prime in there is 3. So I'm going to rewrite 384 as 2 to the 7th times 3. And then 242 we already saw last problem, right? This is 2 times 121, or 2 times 11 squared. Right, so we have this. Square root of, 384 is 2 to the 7th times 3. Then we have u to the 5th times y. Denominator, the 242, is 2 times 11 squared, or 2 times 121, times u squared times y to the 13th. And then I can do some cancellation. See, one of the factors of 2 will cancel, leaving me with 2 to the 6th in the numerator. 2 of the factors of u will cancel, leaving me with u to the 3rd in the numerator. And then a factor of y will cancel, leaving me with y to the 12th in the denominator. And now I'll split it up using the quotient property. Take the square root of the numerator. So that's the square root of 2 to the 6th times 3 times u to the 3rd. That's all that's left in the numerator. Divided by, and then all that's left in the denominator is the square root of 11 squared times y to the 12th. Now those are both perfect squares, right? Those are both something to an even power, so I can easily do that square root. It's the numerator where not all the powers are even, right? So I got to do some splitting up using that product property. So a square root times a square root in the numerator. And the square root of 11 squared times y to the 12th, that would be 11. And then the square root of y to the 12th would be y to the 6th. Right, so I have 11 y to the 6th in the denominator. And then the perfect squares up top, 2 to the 6th is a perfect square. That's something to an even power. 3 to the 1st is not. So that goes in this square root on the right. And then u cubed is u squared, right, a perfect square, times u to the 1st. And then after simplifying completely, the square root of 2 to the 6th would be 2 to the 3rd, which is 8. The square root of u squared would be u. Again, technically it should be the absolute value of u, but they're telling us to assume all the variables are positive, so I don't need the absolute value. Times the square root of 3u. Right, so that's the numerator after simplifying the radical, divided by 11y squared. And there we go. This is as simple as that fraction and square root will get. So in the numerator, 8u times the square root of 3u, and then divided by 11y to the 6th. Great. All right. So this time we're just asked, to simplify this expression. So it is a fraction, right? So if the numerator and denominator have any common factors, I need to get rid of them. But first I'm going to simplify this square root of 216 and then put that back in here, and then we'll simplify the fraction as a whole. So in the numerator I have 20 plus the square root of 216, and then all of that divided by 2. Now off to the side, the square root of 216. 216 is 4 times 54. And in fact, 54, I can break up even more with a perfect square, is 9 times 6. Right, and so I could have actually thought of this as 36 times 6. Right. Yeah, 180 plus 36. So this ends up being 2 times 3 times the square root of 6, which is just 6 times the square root of 6. All right, so I'm going to replace the square root of 216 with 6 times the square root of 6. So 20 plus 6 times the square root of 6 divided by 2. And then you may recall, dividing by a monomial, right? This is a monomial down here. Just divide each term. This is the same thing as 20 divided by 2 plus 6 times the square root of 6 divided by 2. 20 divided by 2 is 10. And then 2 goes into 6 3 times. This ends up being 3 times the square root of 6. Now be careful, don't divide the 2 into this 6 as well, because this is in a square root, the other one is not, right? You can't divide things that aren't in the same root, right? If one expression's in a square root and the other is not, you can't divide them. And then this is it. All right, and please don't add these either. It's like 10 plus 3x. Right, 10 plus 3x. You wouldn't add these together and make 13x, These are not like. One has a square root of 6 attached, the other one does not. So this is as simple as it gets. Now if they both had a square root of 6, right, if it was 10 times the square root of 6 plus 3 times the square root of 6, these would be called like radicals, and then you put them together just like 10x plus 3x and make 13 times the square root of 6. But that's not what's happening here, though. These stay the way they are. All right, so after simplifying the square root of 216 and then dividing everything by 2, I end up with 10 plus 3 times the square root of 6. Alright, so it looks like one more of these. Again, very similar to the last one, where I'll simplify the square root of 192 first, and then divide everything by 4. So here I'm given, in the numerator, 8 plus the square root of 192 divided by all that divided by 4. Right, so off to the side, the square root of 192, I know that 4 goes into this 48 times. Yeah, this would be the square root of 4 times the square root of 48. But 48 is also divisible by 4. It's actually divisible by 16. 16 times 3. This is the square root of 4 times, and then the square root of 48 I can write as the square root of 16 times the square root of 3. So we have 2 times 4 times the square root of 3, so 8 times the square root of 3. And that's going to replace the square root of 192 in this expression. So 8 plus 8 times the square root of 3. And each of these gets divided by 4. But, when you divide 8 by 4, that becomes 2. So 8 divided by 4 is 2, plus, and then 8 times the square root of 3 divided by 4 becomes 2 times the square root of 3. And then, again, these don't go together because they're not like terms. One has a square root of 3 attached, the other one does not. So that's as simple as that gets. So 2 plus 2 times the square root of 3. Excellent. Okay. Back to the quotient property with a perfect square in it. So again, I'll write this out. We'll simplify the fraction first. And I got some space here. So this is the square root. And the expression inside is y to the 7th divided by y to the 21st. Well, this would be the square root of 1 over y to the 14th. Right, the 7 y's would cancel with 7 of those y factors, and you'd be left with 14, 21 minus 7 in the denominator. And then I use the quotient property, right? The square root of 1 divided by the square root of y to the 14th. Remember, this is the positive square root of 1. The principal square root of 1, so this is positive 1 in the numerator. And then the square root of y to the 14th would be y to the 7th, right? Y to the 7th squared would be y to the 14th. And, technically I should put absolute value symbols around this, but they are again saying assume all the variables are greater than 0. So I don't need the absolute value symbols. So there we go. This simplifies to 1 over y to the 7th. Okay. Alright, so another one with this perfect square fraction. Alright, this one I'll just talk out. If you were to simplify the fraction inside the radical here, you'd have 9 in the numerator, and the square root of 9 is 3, divided by, and you'd have m to the 22nd in the denominator, m to the 22, whose square root would be m to the 11th power. And again, technically it should be absolute value of m to the 11th, but they're assuming the variables are positive, so I don't need the absolute value symbol. So the result, after simplifying everything here, would be 3 over m to the 11th. Great. Alright. And a couple more with the quotient property. So again, I'll write this out, and we'll do a bunch of simplifying first, and I'll use the quotient property and then the product property most likely with the numerator. So we're given the square root of 448 times u to the third times y to the third divided by 900 u squared y to the 11th. Alright, so 448, this is 8 times 56, that's 448. 8 I know is 2 to the third power, and then 56 is 8 times 7. So I guess really I could have just said this was 64 times 7. And then 8 is 2 to the third again, and then 7's prime. So we have 2 to the 6th times 7. And if you break it down completely to a product of primes, and then 900, it's 9 times 100, which is 3 squared times 10 squared, but that makes 2 squared and 5 squared. So 900 is, 2 squared times 3 squared times 5 squared. And I guess I should have just said it was 30 squared and then broke up 30 to 2 times 3 times 5. Anyway, so if I'm dividing these, right, let's write out this again. So square root of, the numerator 448 is 2 to the 6th times 7. Then you have that u cubed y cubed. And the denominator 900 is 2 squared times, and then, 3 squared and 5 squared. I'm just going to do this now. That's 9 times 25. That's 225. That's 15 squared. But I noticed that they don't have a factor of 7 or anything. So that's why I'm just going to multiply it out. That's 225, 3 squared times 5 squared. And you got u squared times y to the 11th. Do some simplification here. 2 squared goes away. You're left with 2 to the 4th in the numerator. The u squareds would go. You'd be left with u to the 1st in the numerator. And then y cubed would go from the numerator, and you'd be left with y to the 8th, right? 11 minus 3 in the denominator. So then I apply the quotient rule, and we have the following. Square root of, now 2 to the 4th is 16, so we have 16 times 7. And then times u in the numerator, that's it. And then the denominator, we have the square root of 225, and then all, the y to the 8th left. Y to the 8th. And then I'll apply the product rule. Now the square root of 16, that's 4, times the square root of 7u. Alright, 7u don't have a perfect square factor. And then I said it earlier, the square root of 225, that's 15. And then the square root of y to the 8th would be y to the 4th, right? Y to the 4th squared would be y to the 8th. And there we have it. Right? This is as simple as that fraction and that square root stuff is going to get. So in the numerator, I got 4 times the square root of 7u divided by, and then 15 y to the 4th in the denominator. Great. And I should have just one more like this. Yeah. Okay. So let me go back to my paper. I'll write this out and do all the same stuff I've been doing for all the problems in this objective. So I'm given the square root of some fraction, right, some quotient, 296, u to the 5th, y cubed, and then 242, u squared, y to the 5th in the denominator. Alright, now 296, 4 times 75 would be 300. So this is 4 times 74, right? It's 4 less than 300, one less 4. And that's 280 plus 16. And I know that 4 is 2 squared, right? And 74 is 2 times 37, and 37's prime. So we have 2 to the third times 37, or 8 times 37. Right. And then we've seen 242 earlier. Right? That's just 2 times 11 squared. Right? 2 times 121. So then this is in the numerator, this is in the denominator, right? So the 2's would, one of the 2's would cancel, leaving me with 2 squared up there, or just 4 up here times 37. Then you see the u's, u squared would go away, leaving me with u to the third in the numerator. Y to the third would go away, leaving me with 5 minus 3 u squared in the denominator. So I have the square root of, after all the simplifying, 4 times 37 times u cubed in the numerator. And then again, after all the simplifying, I'd have the square root of 121, or 11 squared, times y squared in the denominator. And once again, the denominator is a perfect square. That's just 11y. And again, it should technically be the absolute value of 11y. But they're telling us to assume the variables are positive numbers, so I don't need the absolute value symbols. Then using the product property up here, we'll do a square root times a square root and put perfect square factors in the left one, non-perfect squares in the right one. 4, 37, and then u cubed I can break up to u squared times u, right? The largest even number less than 3 is 2, so u squared times u. And the square root of 4u squared would be 2u times the square root of 37u. That's the numerator, totally simplified that square root there. And then the denominator, right, all that divided by 11y. And that's as simple as that fraction's getting. So in the numerator, 2u times the square root of 37u, all that divided by 11y. Wonderful. Alright, and that should be it for this preview version of this assignment. Like I said at the top of the video, the questions I saw here may not be the same questions that you see when you work on the assignment yourself, but the objectives are all the same. Right? The structure should be similar. So I'm hoping that watching me do these here helps you out in some way when you work on the assignment yourself. And thank you very much for watching.